Welcome to another video lecture. In this video lecture, we are going to discuss about the time response analysis of the first order system. Now, in the last class, we have already discussed that the transfer function of the first order system is given by 1 upon Ts plus 1, where T is the time constant. Now, here the highest power of the denominator or the characteristic equation is 1. Now, the closed loop representation of first order system is given by this. We have a open loop gain of 1 by Ts, and the feedback gain here is unity 1. This is minus, and this is the input, and this is controlled output Cs. Now, the overall gain of the closed loop system, as we have already discussed, that Cs by Rs is given by Gs upon 1 plus Gs Hs. Now, here the value of Gs is 1 by Ts and a value of Hs is 1. So, when we will put this, we will get this expression here. So, the first order system is defined by 1 by Ts plus 1. Now, to discuss the time response analysis of the first order system, let us take one example. So, here I am taking one example of the first order system RC network. So, in this RC network, we have one resistance and capacitance connected like this, and we have input. Suppose this value is R and this is C, this is resistance, and we have applied some input here, and we are considering this all this in the Laplace domain. So, we have applied input VIS, and we are getting some output VOS. Now, this VIS is the Laplace transform of the input signal VIT, and this VOS is the Laplace transform of the signal VOT. Now, the transfer function of this RC network will be given by the output divided by the input. So, this will be the transfer function. Now, to calculate the transfer function of this RC network, let us assume that there is a current which is flowing. Let us suppose this current is Is. Now, if we apply KVL in the input loop from here to this is the input loop. So, let us apply KVL in this input loop. We will get the equation VIS is equals to drop across the resistance is I into R plus. Now, the value of impedance across the capacitance is XC, and the Laplace domain is given by 1 upon Cs. So, the voltage drop across capacitance will be XC into Is, and value of XC is 1 by Cs. So, I am writing directly here. This is voltage drop across the capacitance will be Is divided by Cs. Now, if we apply KVL in the output loop, this is the output loop. So, if we apply KVL in this output loop, we will get VOS, the voltage drop across these two terminals, is equals to current multiplied by this impedance XC. So, this will be directly Is divided by Cs. Now, in order to get this transfer function, we need to eliminate Is from these two equations. So, I am calculating Is from this equation VOS into Cs, and I am putting this value in this equation. So, I am getting VIS is equals to R into VOS into Cs. I am putting this value Is in this equation, plus again I am putting this value Is VO into S into Cs divided by Cs. These two values will get cancelled, and from this equation we can take VOS common, and can take the ratio VOS by VIS is equals to, this will comes out to be 1 upon this R and Cs will be there, RCS plus 1. So, this is the expression we will get the transfer function of this RC network. Now, remember, the general expression for the first order system was 1 upon Ts plus 1, and if we compare these two expressions, we can say that the time constant value is Rc. the time constant for the system is R into C. Now let us discuss this RC network further. We get the transfer function of this RC network VOS by VIS is equals to 1 by RCS plus 1. Now can we find the response in time domain V0t of this RC network for the unit step signal? So what we try to do here is, let us suppose this is the RC network, and we apply a unit step signal UT instead of VIT, which is the general signal, and what will be the output V0t of this RC network. So we know this transfer function here, and with this we can say that VOS will be given by VIS divided by RCS plus 1. Now we have applied input VIT is equals to UT, which is 1 for t greater than equal to 0, and for t less than 0 it is 0, and we already discussed that the Laplace transform of UT is 1 by s. So what is VIS? VIS, if we take the Laplace transform of this VIT, this will comes out to be 1 by s. So we can put this value here in this equation. So VOS will be given by 1 by s multiplied by RCS plus 1. Now we want to calculate V0t, but we get this value VOS. To calculate VOT, we have to take inverse Laplace of this VOS. Now to calculate the inverse Laplace, we have to do partial fraction of this equation. Let us suppose the partial fraction of this equation is A by S plus B by RCS plus 1. Now we can easily calculate these values A and B. So I'm not going into the details. I'm just writing that we get value A is equals to 1 and B is equals to minus RC. So we can put these values. So VOS is 1 by S minus, I can take minus common, RC and RC I can take common. So let me write it here, RC, RCS plus 1. This can be further simplified to 1 minus R. We can take RC common. So this will be 1 divided by S minus 1 by RC. Or rather this will be plus. Okay, so what is V0t? In this case V0t is the inverse Laplace of VOS. So this is inverse Laplace of 1 by S minus 1 upon S plus 1 by RC. So inverse Laplace of 1 by S is again 1, which is UT, which is 1, and we know that, let me write it here, that 1 upon S plus A inverse Laplace is the of e raised to power minus AT. So I can write it here. So finally V0t comes out to be 1 minus e raised to power minus T upon RC. So this is the final response of this RC network when we apply the unit step signal at the input. So we get the response of this RC network V0t is equals to 1 minus e raised to power minus T upon RC. Let us draw this V0t with respect to time, and let us do further analysis in this. So let me plot this with respect to time V0t. Now if I will start with t is equals to 0. So if I will put t is equal to 0, the response this term will become 1, and the output V0t will be 0. So this will start from 0. Now as I keep on increasing the value of t, I can see that the response V0t will also increase, and at t tends to infinity, let me put t tends to infinity, it approaches to 1. So the maximum value of this V0t can be 1 when t tends to infinite. So this will keep on increasing, this output will keep on increasing, and it approaches to 1 at t when t tends to infinity. So the maximum value it can reach is 1 at t tends to 1. So this is 1. So as we already discussed in the previous class, that when the response of the system stabilizes when t approaches towards infinity, the response is known as the steady state response, and until time when the response is changing with respect to time is the response known as the transient time. So after this time, when system approaches towards infinity and becomes stabilized, so we can say until this time we get the transient response, and after this, when the output stabilizes, we get steady state response. Now in this expression, as we already discussed, that the overall response of control system can be divided in two parts, the steady state response plus the transient response. Now in this expression, V0t is 1 minus e raised to power minus t by RC. This is the steady state response and the steady state value, and this response is the transient response. So overall we get let me summarize this for the first order system. In the first order system, the response is exponential here, as we can see, and system approaches to steady state value as t tends to infinity, and let me give or calculate the values of output at different time. So let us discuss here. At t, V0t, and at t is equal to 0, the output is 0, and at t is equal to RC, different time constant values, the output is 0.63. We will put t is equal to RC, and at t is equal to let's say 3 RC, this value comes out to be 0.95, and when t is 4 RC, the value comes out to be 0.98. So we can clearly see that the value of output approaches very fast towards the steady state value, and at t tends to infinity, it equals to 1. So at t is equal to RC, the output value is 0.63. Hence we can define the time constant from here. The time constant is the time required by system output. Let me write it here. It is the time required by the system output to reach 63% of its final value. The final value is 1, final steady state value. So a time constant basically plays an important role in the control system. Basically it indicates how fast the system tends to reach the final value. If we can say the value of time constant is high, then the system responds very slowly, a slow system, and if the value of time constant is low, that is, we get a fast response. We get fast response from the system. Now let us take one example to understand the first order system. In this example, a system has following transfer function. Transfer function is given 20 by s plus 10, and we need to determine the unit impulse, unit step, and unit ramp response of this system with 0 initial conditions. So how to solve these type of problems in the control system? Now it is given that Cs by Rs is 20 divided by s plus 10. We have to calculate Cs for different inputs, unit impulse, unit step, and unit ramp. So the value of Cs from this expression is 20 Rs divided by s plus 10. Now in the first case, when unit impulse signal is given, the value of Rs will be 1, since the Laplace transform of the unit impulse is 1. So in this case, the value of Cs comes out to be 20 divided by s plus 10, and we need to calculate the value of Ct, which is the inverse Laplace of Cs, which is the inverse Laplace of 20 divided by s plus 10. So as we already discussed that the inverse Laplace of 1 upon s plus a is e raised to power minus at. So the inverse Laplace of this will comes out to be 20 e raised to power minus 10 into t. So in the first part, the response of this system will be 20 e raised to power minus t. Again, this is a pure exponential signal. Now in the second part, the signal is given as unit step, So in this case, the value of Rs will be 1 by S. So the value of Cs in this case will be 20 divided by S plus 10, because the value of Rs is 1 by S. So we will put 1 by S in this equation. So we will get this. Now we cannot determine the inverse Laplace of this expression directly. We need to do the partial fraction first. So this will be, let us suppose the partial fraction is A by S plus B by S plus 10, and after you can easily determine the value of these constants. Let me write it directly. So the value of A will comes out to be 2, and this is S plus, and the value of B will comes out to be minus 2, S plus 10. Now you can take the inverse Laplace of this. So Ct is the inverse Laplace of 2 by S minus 2 by S plus 10. So you will get the inverse Laplace of this is 2 minus 2 e raised to power minus 10t. Again, this signal is purely exponential. This is the steady state value, and again you are getting the exponential value. Now in the third case, a unit ramp signal is given. Unit ramp signal is given. So value of Rs in this case will be 1 by S square. So again the value of Cs will be 220 S square S plus 10. Again we will put the value of Rs in this equation. So this time it is 1 by S square. So we will get this value. Now again we have to do the partial fraction. This time the partial fraction will be A by S plus B by let us suppose this is A by S square, B by S plus C by S plus 10. So you can easily determine these values A, B and C. So when you will calculate these values, A will come out to be 2, B will come out to be 0.2 minus 0.2, and C will come out to be 0.2. When you will put these values and take the inverse Laplace, you can finally get the value of Ct, which comes out to be 2t minus 0.2 plus 0.2 e raised to power minus 10 into t. So again this is exponential with the steady state value and this value 2t. So with this example, it is understood that for different inputs, whether it is impulse, step or unit ramp, the response of first order system is always exponential. So I hope you understood this the example. Thank you.